Physical rehabilitation exercises are vital for recovery from conditions like stroke, Parkinson's, and back pain. Traditionally, patients rely on health professionals for guidance and assessment. However, many perform these exercises at home, often without expert supervision. This creates a gap in feedback and evaluation, making it difficult for patients to know if they're doing the exercises correctly. Recent advances in technology aim to bridge this gap by providing automatic assessment tools. In this video, we explore how artificial intelligence, specifically graph convolutional networks, is revolutionizing the way rehabilitation exercises are evaluated, offering real-time feedback and guidance for better outcomes. Patients perform rehabilitation exercises alone. They often lack the ability to assess their performance accurately. Traditional methods require expert observation, which is not always feasible, especially for home-based therapy. This leads to uncertainty about exercise correctness and progress. Moreover, existing automated systems are limited, often relying on fixed-length input or handcrafted features that require extensive pre-processing and expert knowledge. These limitations hinder the effectiveness and accessibility of rehabilitation assessment, highlighting the need for smarter, more flexible solutions. Deep learning has emerged as a powerful tool for analyzing complex data, including videos of rehabilitation exercises. Early approaches used convolutional neural networks (CNNs) to extract features from skeleton data representing body joints. While CNNs improved automation, they struggled to capture rich spatiotemporal features, especially from variable-length inputs. This means they couldn't fully understand the dynamic movements and subtle improvements in patient performance. As a result, researchers began exploring more advanced models that could handle these challenges and provide more accurate assessments. Graph convolutional networks (GCNs) offer a novel approach to modeling human movement for rehabilitation assessment. Unlike CNNs, GCNs treat skeleton data as graphs where body joints are nodes and their connections are edges. This allows the model to capture the topological structure of the human body and extract meaningful features from interactions among neighboring joints. By leveraging GCNs, researchers can analyze variable-length exercise videos and provide continuous assessment scores, offering a more nuanced understanding of patient performance. Spatiotemporal GCNs, STGCNs, extend the basic GCN framework by incorporating both spatial and temporal information. This means the model not only understands the structure of the body at each frame but also tracks how movements evolve over time. STGCNs were initially used in traffic forecasting but have proven effective in action, gesture, and emotion classification. For rehabilitation assessment, STGCNs can predict continuous scores, adapting to variable-length inputs and capturing the complexity of human motion during exercises. Most traditional models classify exercises as simply correct or incorrect, which fails to capture subtle improvements in patient performance. Continuous assessment, on the other hand, assigns a quality score to each exercise, reflecting how closely the movement matches the prescribed version. This approach enables more precise monitoring of progress and provides actionable feedback for patients. By predicting continuous scores, advanced models can guide users to improve their performance over time, rather than just flagging errors. One of the major challenges in rehabilitation assessment is handling variable-length input. Patients and experts may perform the same exercise at different speeds or with varying repetitions. Traditional models require fixed-length input, limiting their flexibility. The proposed GCN-based model processes variable-length data, allowing users to perform exercises at their own pace. This adaptability ensures that the assessment is accurate regardless of how long or how many times the exercise is performed. Self-attention mechanism is a key innovation in the proposed model. It dynamically calculates the importance of each body joint during an exercise, guiding the user to focus on movements that matter most for assessment. By analyzing attention weights, the model identifies which joints contribute more to the final score. This personalized guidance helps patients understand where to improve, matching the attention patterns of expert users for better results in future trials. Validate the effectiveness of the GCN-based assessment model. Researchers use two established datasets, KI-MORI and UIPRMD. KI-MORI includes RGBD videos and ground truth scores for 5 types of exercises, featuring both healthy subjects and those with chronic motor disabilities. UIPRMD contains 10 rehabilitation exercises performed by healthy subjects, with detailed joint positions and angle. These datasets provide a robust foundation for training and testing the model, ensuring its reliability across diverse environments. Advanced RGBD cameras and pose estimation algorithms make it easy to obtain skeleton data, representing the coordinates of body joints. This data forms the basis for modeling human movement in rehabilitation exercises. By treating each joint as a node in a graph, the GCN framework can analyze the spatial relationships and extract features that reflect the quality of movement. This approach is both cost-effective and accessible, enabling real-time assessment in various settings. Core Solution Framework uses graph convolutional networks to represent human skeleton data as graphs. This allows the model to extract features from the topological structure of neighboring body joints. The final design incorporates spatiotemporal GCNs to unify spatial and temporal feature extraction. By addressing challenges like variable-length processing and explicit guidance, the model adapts to diverse users and environments, providing accurate assessment regardless of exercise pace or repetition. A vanilla STGCN can provide a baseline assessment score. It has limitations. The global pooling layer before fully connected layers ignores sequential dependencies among spatiotemporal features. This means users performing the same exercise at different paces may receive inconsistent scores. Additionally, vanilla SDGCN treats all body joints equally, failing to account for the varying importance of joints in different exercises. These issues highlight the need for further model enhancements. To address the limitations of vanilla SDGCN, the model integrates LSTM layers instead of global pooling. LSTM captures sequential dependencies in spatiotemporal feature vectors, extracting discriminative features accumulated over time. This is crucial for assessing criteria like smoothness, which depends on velocity and acceleration across frames. By using LSTM, the model preserves the sequential nature of data, enabling variable length processing and more accurate assessment. Different joints play varying roles in each exercise. For example, squatting emphasizes the ankle, knee, spine, and shoulder, while arm lifting focuses on the elbow, spine, thumb, and wrist. The model implements a self-attention module, treating each joint differently based on spatial and temporal context. By dynamically calculating the role of individual joints, the model guides users to focus on movements that impact their assessment score the most. Self-attention map highlights the role of body joints during exercises. Larger attention values indicate greater emphasis on specific joints. By comparing attention patterns between expert and patient users, the model identifies which joints patients should focus on to improve their scores. This visualization provides actionable guidance, helping users understand how to adjust their movements for better performance. Model uses Huber loss during training, which combines the benefits of mean squared error and mean absolute deviation. Huber loss is less sensitive to outliers, making it ideal for noisy or incomplete skeleton data. This ensures that the model remains robust even when some joint positions are disturbed, maintaining reliable assessment performance across diverse data sources. Proposed model is designed for real-time assessment, with efficient training and testing times. Using a single Tesla K80 GPU, the model can process skeleton data quickly, making it suitable for real-time feedback during rehabilitation exercises. This computational efficiency ensures that patients and therapists can receive immediate guidance, enhancing the effectiveness of home-based therapy. Model performance is evaluated using mean absolute deviation MAD, mean absolute percentage error MAP, and root mean square error RMSE. These metrics measure the accuracy of predicted scores compared to ground truth, with lower values indicating better results. By using multiple metrics, researchers ensure comprehensive evaluation of the model's effectiveness in assessing rehabilitation exercises. Optimize model performance, researchers conduct hyperparameter tuning on a validation set. Parameters like hop size, number of SDGCN blocks, and stacked LSTM layers are adjusted to achieve the best results. This careful tuning ensures that the model balances complexity and accuracy, providing reliable assessment across different exercises and user groups. GCN-based model achieves state-of-the-art performance on both KIMORE and UIPRMD datasets. Compared to previous methods, it provides more accurate assessment scores, thanks to its ability to capture spatiotemporal features and dynamically guide users. This success demonstrates the potential of advanced AI models in transforming rehabilitation assessment and improving patient outcomes. Relation studies reveal the impact of different model components. Stacked GCNs improve feature extraction, while concatenated temporal convolution outputs enhance performance by considering temporal information. Replacing global pooling with LSTM further boosts accuracy, and the self-attention mechanism provides the best results by dynamically calculating joint roles. These findings highlight the importance of each component in achieving optimal assessment. Feature visualization using TSNE plots shows that the model extracts similar representations from different input lengths. This means the model can assess exercises performed at varying speeds and repetitions, maintaining consistency in evaluation. Such visualization confirms the model's adaptability and robustness, ensuring reliable assessment for all users. Model analyzes the natural topological structure of the human body, extracting spatial information using attention-guided graph convolution. This allows it to treat each joint differently based on the exercise. For example, in arm lifting, the elbow and wrist are emphasized, while pelvis rotation focuses on the spine, base, and wrist. These findings align with medical professionals' recommendations, validating the model's guidance. Model's performance is validated using different pose estimation algorithms, including Microsoft KineTV2, Blaze Pose, and Video Pose 3D KineTV2, which uses RGBD information, outperforms RGB-based algorithms, providing more accurate joint detection. This demonstrates the importance of high-quality skeleton data for reliable rehabilitation assessment. With efficient computational design and robust pose estimation, the GCN-based model can provide real-time assessment of rehabilitation exercises. This capability is crucial for home-based therapy, enabling patients to receive immediate feedback and adjust their movements accordingly. Real-time guidance enhances motivation and ensures exercises are performed correctly, accelerating recovery. By analyzing attention maps and joint roles, the model provides explicit guidance to patients. It identifies which body joints to emphasize for better scores, helping users match the movement patterns of expert therapists. This personalized feedback empowers patients to improve their performance, making rehabilitation more effective and engaging. Compared to previous models, the GCN-based approach offers several advantages. It supports variable length input, captures spatiotemporal features, and provides explicit guidance through self-attention. Previous methods relied on handcrafted features or fixed length input, limiting their flexibility and accuracy. The new model sets a benchmark for automated rehabilitation assessment. Medical professionals play a crucial role in designing and validating rehabilitation exercises. The model's guidance aligns with expert recommendations, ensuring that automated assessment supports clinical best practices. By integrating AI with medical expertise, the system enhances the quality and effectiveness of rehabilitation therapy. As technology advances, rehabilitation assessment models will continue to evolve. Future research may focus on integrating multimodal data, such as audio and video, improving pose estimation accuracy, and expanding guidance to cover a wider range of exercises and conditions. The goal is to make rehabilitation accessible, effective, and personalized for all patients. Summary: graph convolutional networks provide a powerful framework for assessing physical rehabilitation exercises. By capturing spatiotemporal features and guiding users through self-attention, the model delivers accurate, real-time feedback. This innovation bridges the gap between home-based therapy and expert supervision, empowering patients to achieve better outcomes and supporting health professionals in monitoring progress. This research is supported by the Information and Communication Technology Division, Ministry of Posts, Telecommunications and Information Technology of Bangladesh, and the University of Dhaka. The contributions of Swakshar Deb, M. Fakhrul Islam, Shafin Rahman, and Sejidi Rahman are acknowledged. The datasets used include KI-MORE and UIPRMD, and the model implementation follows best practices in deep learning and pose estimation. Use the GCN-based assessment model. Patients or therapists record exercise videos using RGBD cameras or pose estimation algorithms. The skeleton data is extracted and fed into the model, which processes the input and predicts a continuous assessment score. Attention maps highlight joint roles, providing guidance for improvement. The system can be integrated into home-based therapy platforms for real-time feedback. Patients benefit from automated assessment by receiving immediate objective feedback on their exercise performance. The model identifies areas for improvement, helping users focus on movements that matter most. This personalized guidance increases motivation, ensures correct execution, and accelerates recovery, making rehabilitation more accessible and effective. Therapists can monitor patient progress remotely, using automated assessment scores and attention maps to identify strengths and weaknesses. This enables more efficient follow-up, targeted interventions, and data-driven decision-making. By leveraging AI, therapists can extend their reach and support more patients, improving overall rehabilitation outcomes. GCN-based model can be integrated into home therapy platforms, allowing patients to perform exercises independently while receiving real-time feedback. This integration supports continuous monitoring, personalized guidance, and progress tracking, making rehabilitation more convenient and effective for users outside clinical settings. Data privacy is essential in automated rehabilitation assessment. The model processes skeleton data, which can be anonymized to protect patient identity. Secure data handling and compliance with privacy regulations ensure that patient information remains confidential, fostering trust in technology-assisted therapy. The model's flexible architecture allows it to be adapted for new rehabilitation exercises and conditions. By training on additional datasets and incorporating expert feedback, the system can support a wider range of movements, making it valuable for diverse patient populations and therapy goals. A user-friendly interface is crucial for widespread adoption. The model can be integrated into apps or web platforms, providing intuitive controls, clear feedback, and visualizations of attention maps. This makes it easy for patients and therapists to interact with the system and understand assessment results. The model supports continuous improvement by tracking patient progress over time. Assessment scores and attention maps provide insights into performance trends, enabling users to set goals and measure achievements. This ongoing feedback loop motivates patients and supports long-term rehabilitation success. Collaboration between AI researchers, medical professionals, and therapists is key to advancing rehabilitation assessment. By sharing data, insights, and best practices, the community can refine models, validate guidance, and ensure that technology meets clinical needs. This collaborative approach drives innovation and improves patient care. Adopting automated assessment in rehabilitation faces barriers such as technology access, user training, and data quality. Addressing these challenges requires affordable devices, educational resources, and robust pose estimation algorithms. By overcoming barriers, the system can reach more patients and deliver effective therapy worldwide. Automated rehabilitation assessment has the potential for global impact, improving access to therapy in remote and underserved areas. By leveraging AI and digital platforms, patients everywhere can benefit from expert guidance, real-time feedback, and personalized rehabilitation, regardless of location. Real-world patient stories illustrate the benefits of automated assessment. Patients report increased motivation, faster recovery, and greater confidence in their exercises. Therapists note improved monitoring and targeted interventions. These testimonials highlight the transformative power of AI in rehabilitation. Healthcare providers, researchers, and technology developers are encouraged to collaborate and innovate in automated rehabilitation assessment. By advancing AI models, improving data quality, and integrating user feedback, the community can make rehabilitation more effective, accessible, and personalized for all. future of rehabilitation is bright with AI-powered assessment tools. By combining advanced models like GCNs with real-time feedback and expert guidance, patients can achieve better outcomes and therapists can monitor progress efficiently. This synergy between technology and healthcare promises a new era of personalized, effective rehabilitation for everyone.